Moving along, let's talk about the positions of Sun, Earth, and Moon now. We're going to refer to this now as just the Moon's motions. Well, big thing we want to point out here is that the Moon is, as we say, tidally locked to the Earth. What do you mean? Imagine there's this arrow, and that's fixed to the same point of space on the Moon. And you let the Moon rotate around. Right? Comes around. The arrow, representing the same point on the Moon, is always facing the Earth. That's tidally locked. The same face of the Moon is always pointing at us. And notice what this means in terms of a light side of the Moon versus a dark side. We only see one face of the Moon. We call this a synchronous orbit. As the Moon is rotating around its axis, it's also orbiting Earth, and the Moon's rotation is equal to its orbital period. So, this leads us to say that there is no dark side of the Moon. Here's the dark side of the Moon, and it represents the same point in space. Watch this. Doop, doop, doop. Now it's fully illuminated. So there's no such thing as a side of the Moon that's in perpetual darkness. It's just a side that we don't see. We could call it the far side of the Moon. We don't get to see the far side of the Moon. We always see the near side due to that tidal locking. And going along with that, that tidal lock creates that half the Moon will be always bright, half the Moon will be always dark. Sun coming in, shining in, just half the Moon. But we see the phases of the Moon. So what phase we see of the Moon determines the angular position. So let's go through the phases together now. We'll start at new Moon. So the orientation now is that there's Sun out here radiating light, and it goes Sun, Moon, Earth. And from Earth's perspective, we see a dark Moon, new Moon, completely blackened. Then we go down to a waxing crescent, right? You see this crescent shape, and the light's coming in from the right side, starting to illuminate it. We'll reach the first quarter. First quarter being half the Moon is illuminated. Quarter refers to the period, the orbit. So quarter, half, 3/4, back home. So half the Moon is illuminated at the first quarter, and it'll be that right half. Now we get to the waxing gibbous, right? When we say waxing crescent, waxing gibbous, think of wax on. You Karate Kids fan out there, we're waxing on the light. Finally, we'll get to the full Moon. The position is Sun, Earth, Moon, and we get to see the Moon fully illuminated. It's completely bright. And keep going, complete the cycle. Now we're going to reach a waning gibbous. So we wax the light on, we wane the light off. And we'll see the dark side of the Moon on the right portion. Keep going, get to that third quarter where it's half illuminated, half dark. Finally reach that waning crescent. So the remaining bit of the illuminated Moon is that left side. And so we finally come back around to our new Moon, and a month has passed by. To recap, we say that at full Moon, the brightness on the Moon will begin to wane off. At the new Moon, it will wax on. And for perspective from the northern hemisphere, we say the light will wane on from right to left, right to left, right to left. And then it will start to fade right to left. The fading is from the right going to the left. To recap that orbital period, the Moon takes 27.3 days to orbit once around with respect to the stars. Lunar phases repeat every 29.5 days. This is a strange concept we have to wrap our heads around. There are two types of period. There is a sidereal period and a synodic period. And this will come back again in the next section, so I'll wait for fully defining them there. What matters here in terms of the Moon is that we can say the rotational periods are equal to the sidereal periods. That tidally locked aspect of the Moon, one face of the Moon, is always facing us. Now another thing that astronomers have done, or humans have done throughout history is try to make calendars. Obvious things to use for calendars are orbits of the moon. It's a very repeating cycle every 27 days. We also use the positions of the sun. So different societies have come up with different calendars. It's a little difficult. Our current calendar, the Gregorian calendar, uses 365 days, but our orbit around the sun is actually 0.256 days. So that's why we have leap years. We need the leap year to account for that quarter day that's missed in our orbit around the sun.